All right. A number of students have come to me asking what the hell they should study, how is it doing. Let me tell you that don't worry. The students all think the exam is going to be difficult. It will be somewhat difficult, but it's all going to be qualitative. We're not going to ask you to do any calculations of the sort that you've done on your homework. Yeah?
Will we get the equation sheet before the exam?
Yes, we should hand that out today. Okay, remind me if I don't. Isaac, we better get the equation sheet out to the students today. Yeah. Okay. The exam is, this course is graded on a curve. That means you don't have to get 90% to score an A, like you did in high school. A is probably going to be something like 70%. All right? If you don't think you understand everything now, don't worry. The person sitting next to you doesn't understand it either. I know that you think it's such a hard course. A lot of students have dropped the course because of the hard, quote-unquote, homework I've asked you to do, but I'm glad to see that you did not. It's just to teach you how to think in a way that uses math, but doesn't religiously do goddamn calculations on the stupid calculator. All right, now the first exam is going to be in 120 Latimer. I believe that is a chemistry building. Am I right there? Yeah, a chemistry building. It's uphill from us, a few buildings. All right, 120 is a big enough room, I believe, that we can spread out when we get there. Yes?
Is it at 6 or 7?
Sorry?
Is the gym at 6 o'clock or 7?
Wait a second.
Eric told me 7 to 9.
Oh.
That's when you have to research.
7 to 9?
Yeah.
Oh, sorry. 7. That's wrong. Sorry. 7 to 9. Excuse me. 7 to 9. My mistake.
I'm checking right now. But yeah, I think it's the room is reserved 7 to 9.
All right. 7 to 9. Excuse me. This is wrong. Okay. All right. Let's go on. Now, the exam will cover the material we've done through last week. There will be some exam. There will be very light questioning of today's lecture. Lecture I give on Thursday will not count on the exam. All right? Yes?
We have class on Thursday.
Yes. Yes, that's why the exam's at night. I have the material is in this course is more than can be offered in the number of classes plus exams you have. So the exams are at night, the material is taught during the day. Okay. Now, today we're going to talk about measuring stars, looking at stars very closely and finding evidence that they contain planets about them. So we're going to look for extragalactic, extrasolar planets. This is a map showing the sun, and it shows the region of the sky, a region of the Milky Way that it is looking for planets in this region, and we'll talk about that toward the end of the lecture. This is known as the Kepler mission, after you-know-who. Okay, now, the major thing to note is that as Jupiter, or a heavy planet, orbits the sun, it's just like a teeter-totter. You know, in a teeter-totter, when you're going with your young sister, young brother, young cousin or something, little kid, you can't balance him unless he's at the far end of the teeter-totter and you're close to the fulcrum. If you're close to the fulcrum, you can roughly balance him, sort of, and the teeter-totter will be even. By the way, you all know teeter-totters, right? They aren't thrown out by being too dangerous, are they? Good. Okay. So All right, so teeter-totters, the heavy person has to be near the center of mass of the system. What happens is that Jupiter orbits around in a circular orbit of the type we've said. And I didn't tell you that Kepler's law is not quite right. It's missing a term. Because the sun is not stationary at that point, here's the teeter-totter at the center of mass. The sun rotates around as well. So Jupiter orbits around and the sun orbits around. Jupiter gets over here and the sun's over there. And it actually orbits the center of mass every 12 years. It does not orbit the position of the star. All right, and let me show you examples of this. Okay, here is a star orbiting another star, and they're orbiting about the center of mass. Here's one. This one weighs four times the mass of the sun. This one weighs 16 times the mass of the sun. So let me adjust them. If I make it about the same, roughly about 16 almost, the two one of them is not primary. They're both orbiting the center of mass. This is equal mass on the teeter-totter. All right? And they're not primary. Okay? So this is the concept of center of mass motion. If I bring one up and the other down, you get this. Notice that the orbit is faster now. Okay? So the combination of the two of them satisfies Kepler's law. But Kepler's law is really applied to the center of mass. And in the solar system, the center, remember that Jupiter weighs 100th that of the sun, so it's a very small correction. And nobody noticed it in those days. All right? So this is the reality. Okay. So binary systems suppose the binary system is dark. This is a dark star, say, or a planet. We know that the center of mass has to move for the binary system. And we can detect the motion of the center of mass. And that's one of the techniques that's used. Okay, so, all right, now, how do we detect these extrasolar planets? Can we see the extrasolar planets if we look at a telescope? And the answer is no, because the planets are very small, and unless the star is extremely close to us, we can't see it. Okay, so we don't see it. All right, distance is remember, the distance to stars is something measured as parsecs, and a parsec is 200,000 light years. No, I'm sorry, a parsec is 3 light years, and that amounts to 200,000 astronomical units. So the stars are so far away that you really can't see them. You can't see the planets that might be there. Okay, that means that because they're so far away, the angles are too hard to resolve with their biggest telescopes, and the stars are very bright, making it very difficult. Okay, so what you see is the motion of a planet around, and the star is orbiting as well, and when the star is coming toward you, the light gets blue shifted. When the star is moving away from us, the light is red shifted. What you will see is as a function of phase, for example, this is measured in time of days, and it measures, you think that this is a velocity, And how fast is it moving? Well, you measure something like plus or minus 50 meters a second. That's running, pretty fast. I mean, that's 100 meters in 2 seconds. That's faster than anybody can run. And so it's a fast clip. That is measurable. Believe it or not, that is not too small of a signal to be measurable. But that is the sort of signal you're looking for on these planets. And this is extremely difficult. All right, so let's look at this. A few more problems to look at. Okay. So here's a planet orbiting a star. It's orbiting in the center of mass. Okay, the star is orbiting around a small circle. Now, what we're doing here is we're blowing up a red line. So this is a close-up of the spectrum. See, it's 6547.199, 6547.2. Well, this is a very small difference. You have to do this with high resolution, it's called. That means fine division of the line. And look at what happens. As the star moves, the line moves back and forth. So if you've got a spectrograph that can resolve the light down to very fine signals, you can measure that it is moving because of binary orbit around it. So this is oscillating like that. And the Earth, the Sun, has a measurable measure. Now, for example, when the Earth moves, its weight compared to the Sun is very small. So the Sun moves only a small amount, and that's below the signal noise that you can pick up with this type of technique. Now, if you replace the Earth with, say, the Jupiter, you put a Jupiter in place of the Earth at the same position of the Earth, it rotates very much faster. It does not rotate faster. To balance it, the star has to be offset further from the center of mass. Okay, so it's a bigger circle, and it's moving faster because it's going to have the same period. So the bigger the planet, the easier the signal to detect. The smaller the planet, it gets very difficult. These techniques have been done mostly by Jeff Marcy in our department, astronomy department, Berkeley, using the Keck telescope, world's biggest telescope. And with that, they have amazing data on hundreds of objects. I'll show you more about it. Okay. Now, okay, so here's a signal. Oh, wait a minute, I'm going to turn some of these lights off. Oh, listen, I don't know if I said this. These guys, Saul's a professor of physics. He was a postdoc here. He worked with me and with Alex Filipenko. This guy is from Australia. These three fellows won a Nobel Prize in physics, announced this morning. Physics Nobel Prize. And they won it for discovery of the dark energy. Now, what is dark energy? I'll tell you later. I'll tell you all about dark energy at the end of the course, but I can't tell you now. That would spoil everything. So let's wait till we get there. All right. So now here's an example. A binary system exists out there, and with this, and you can measure the spectrum of this guy, and you measure coming and going. And here's the crosses are the data points that are taken of the object. All right, now what can you do? Well, we could try. Here are parameters we can change. We could change the orbital radius of this orbiting star, or we can change its mass. And we're going to see how much this varies. So suppose I change the orbital radius. Well, that doesn't look very good. You probably want it small. If I change the mass of that, well, that's no good. You want it about here. So suppose you keep changing. Ha! Is that right? Yeah, that's pretty good. All right, so this, by fitting the line to the data finally says, oh, well, for these parameters, it's a pretty good fit. The parameters are that the separation is 0.7 astronomical units. The mass of the orbiting planet is 4.4 times the mass of Jupiter. And that's how you do it. You collect a lot of data, and the data is star's speed of the motion of the star, and it's measured in meters per second, 150, 150. If it moves that fast, then it is a binary star. I mean, it is a star probably of the mass of Jupiter. And this technique can be used for anything in there. Now, is that clear? You understand what I've done? I've fit the parameters of the Kepler's law. Kepler's law depends on the mass, depends on the separation. Here's the separation, here's the mass. Okay, you fit them, and out comes the answer. You're fitting the data to these parameters in there. All right. Well, let's see. Let's see what I've got here. This was plot 1. I'm not sure what this will do. Plot 2. Okay, let's try another case. Here's another situation. Wow. This is a weird case. All right. This is obviously a terrible fit. How about this? I don't think this fit is good enough. Well, that's terrible too. I think there's something wrong here. So none of these fits are going to be acceptable. The mass. This one? Increase the other one? Right there? Okay, see here, these guys know how to fit this. Well, what about these points? There's nothing here. All right, well, it fits that data, but it doesn't, I don't know why it didn't, they don't have data here, I suppose. Okay, well, there's no data. So where there's no data, you can draw a wiggly line. You can't rule it out, so it must be acceptable. All right, so this that's the parameters. Okay. So you can have fun. This is what Jeff does. Okay. Okay, so here are some nearby stars, and they're fitting. Here's one. This is a very odd star, but this is a star that's not on a circular orbit. If it's off a circular orbit, the star's signature here looks a little strange. But it's okay. He can fit them all. So these are stars for all these fits. And he gets, from them, he can from them and moving the planet's motion, he learns what the mass is of the planets orbiting stars. It's amazing. All right, now how does this work? All right, now this is something I'm not going to expect everybody to know this, but I'll just tell you what he does. Here, a star has a mass m, period of the orbit, velocity of the star is what we measure, period, and velocity. Those are the two dials on the two parameters. How do we use them? All right, we use it the following way. P squared equals 4 pi squared a cubed over g mm. This is the proper way of writing the Kepler's law. And the mass is much bigger than the mass little m. Little m is the mass of the planet. Capital M is the mass of the star. So that means that you can solve for A, and A is written as gm p squared over 4 pi squared to the 1/3 power. Center of mass equation is that if you're going to balance the star, that means the velocity of u, the mass of the star, times your mass times the mass of the star equals mass of the planet times the velocity of the planet. Velocity of the planet you put is equal to, it's equal to 2 pi times the semi-major axis. This is the circumference divided by the period. That gives us in the units of velocity. From form 4, we have this. We substitute m into there. And you can, just with a measurement of P and V star, you can measure the mass m and the size a around neighboring stars. So all the information is there, and this is routinely done. Now, this is his web page. You can find beautiful stuff on his web page. Go look at it. These are the first results showing here's one astronomical unit. That's our radius. 2, 3, 4, 5. Out here is Jupiter. Okay, and these are the planets that he sees, less than 1 solar mass. Suppose you look at greater than 10 solar masses. He's found planets here, here, here. Amazingly hot, and these are closer. These are giant planets, bigger than that of Jupiter, and they're very close to the star. Very different from our solar system. Incredibly different. If you took Jupiter and put it in that close, it would become very hot. It would swell up and become a hot Jupiter. All right, that's a hot Jupiter. This is how they make a hot Jupiter. You bring it in close to the star, and it swells up. This was a surprise when it was first discovered. People didn't really believe it, and they couldn't see how to do that. But now they feel it can be done. It's difficult, but it can be done. These are the orbits of extrasolar planets. For example, here is Jupiter's orbit about our sun. Here's the orbits of lots of little things. Lots of crazy orbits obscene. All right. Now, okay, this is a summary of the results. The orbital distance from 1/10 of 1/100th to 1/10 1/1000, the logarithmic scale of distance. Here is the habitable zone. Right here is the habitable zone. And here are the masses of the planets and the orbit of the planet from the star. Look at all these planets he's seen, and most of them are really, really massive, 100 times the mass of the Earth, 10 times, 1,000 times. They're all generally very close. Why are they very close? Because of a selection effect. If a heavy planet is close to the star, it's really whizzing around and making the star have a large velocity of Doppler motion. This teeter-totter moves fast, and that makes it easier to detect. As it is, Jeff Marcy only sees about 8% of the stars have a signal. The rest of them don't have any signal he can determine. That would mean like Earth-like planets orbiting those stars are really not detectable easily. So he gives up on them after a while, and he can't see them. In other words, there's a big selection effect against finding objects down here. Very difficult to do. But there's no selection effect against finding objects there. So, okay, don't worry about what he's seen. It isn't necessarily true of the universe. Here is our solar system, Saturn, Jupiter, Uranus, Neptune. And they see a few planets that are about like Jupiter. Okay. Now, 8%, I said, 8% of stars have detected planets. All right? Why don't you think about what this means? Why does that happen? Large planets easier to detect. Are they generally enclosed, old and spiraled in? All right? Which is it? Is it A? All right, somebody's shaking their head yes. They're easier to detect. It is not that they're in close. They are in close. The ones we see are in close, but that may not be typical of all the stars in our galaxy. All right, the systems are old. Large planets spiraled in? No. If they spiraled in, they spiraled fairly quickly. It's not something that happens because the star is old and tired. It's tired of circling around and just going to spiral in, gets tired and falls in. No, that doesn't work that way. If there's energy conserved, it's conserved, and it's going to be the same orbit it's had forever. There's no extra force acting on the planets, the large planets that have hydrogen and helium. No. They're attracted by gravity, the same as all the other planets. Okay. So the stars that are orbiting close together are these hot Jupiters. And some of them are very elliptical. These were two surprises that the community faced when this data was first public. But that is the surprise. Okay, now, let's look at another type of technique. Suppose a star goes right in front of the planet. If the star goes in front of the planet, it will occult part of the planet's light. And here, for example, the star, here's versus time in hours. It's all consistent with nothing, and then it goes down like this, consistent with nothing. That is a signature of a star blocking the light of a planet. All right, let's take a look and see how this works. Okay, so let us turn it on. And now there's a star. Oop, it went in front of it. And there it goes out. Okay, so it occulted the planet for a short time. Now, you can't see this occultation. You don't know when it's going to occur unless you look at it. You have to stare at these pictures and let it go for days and days and days and days and days. And after all, if you're looking for an Earth-like planet, we would only occult the sun once a year. You really have to look at it for a while to see it. Okay, now let's see what we see here. This was 5 times the radius of Jupiter. Let's try 2 times the radius of Jupiter. Begin the signal. Now notice that even though it's only 2 times the radius of Jupiter, that planet that dialed it in, the light going through is 95%. That is to say, it only occults 5% of the light. It's not very much. So you have to look at the planet, look at the star, and measure the star's brightness to very good precision. If you can't measure it to better than 1% precision, you're not doing very well. All right, now let's try this again. Okay, so here's another case. This is one that he had to measure to 1% precision in order to see it. That is pretty fine. That is difficult to do from the ground. You can't do this type of experiment from the ground because the atmosphere is flickering. The clouds come by and they absorb 1 or 2% of the light and reflect it around, and you can't control it well enough. So generally, you want to do these projects in space if you can. Okay. All right, suppose if the planet falls to 1% of the size of what it had, all right, you measure the sizes of relative planets, and that's what you do with this technique. Okay, Jupiter is 5 astronomical units. It's 130 degrees from the heating of the sun, etc. But hot Jupiters, they can get as close as 3/100ths of an astronomical unit. It's crazy. Some of them have really short orbits, and it's amazing if they do. All right, how do the stars get so close? How can Jupiter ever get so close to the planet, to the star? Here's the thought. Here is Jupiter that's in a forming solar system. Here's the proto-sun, and Jupiter there's a cloud out here, and the cloud has aspherical distribution. That is to say, it can pull on Jupiter and pull it in. The material bunches up because of that, and it does enable itself to pull itself in. It's not certain how this works, but it is a topic of current research. Okay, now, all right, I want you to talk to your neighbor and think of what the answer to this is. What happens in a gravitational encounter that allows the planet's orbit to move inward? Is it transferring energy and angular momentum to another object? Is the gravity of the central star forcing the planet to move in? Or is it gaining mass from another object, causing its gravitational pull to move in, its gravity to be larger? All right, so think about what answer you'll have here. And yes?
Are these kind of questions the midterm questions?
No, this is too hard. No, by the way, I would suggest, if you're looking for problems to study, at the end of the chapters are problems, deserves further contemplation. Read them over. Don't worry about all the details in the chapter. Read over these problems and be comfortable with them. If you're comfortable with them, you're in good shape. Okay? All right. So red, green, blue. Red, green, and blue. What's what? Come on, you guys about to talk. Let's hear some talking. I don't hear any talking. You're quiet. Okay. Let's hold up your answer. Red, green, or blue? I only see a few of these. I see a variety of answers. All right. The correct answer is A, red. Now, how does it do this? I'll tell you what it doesn't do. The mass from the gravitational pull indeed becomes stronger if it picks up more mass. But it is a consequence of the shape, the functional form of the relativity, the gravity, that it won't really change its orbit correctly. The material it absorbed was moving in about the same orbit. It doesn't change the overall characteristic of it. So you say, if you have a planet, if you have a planetesimal and it hits another planetesimal, forming a bigger object, it doesn't change its orbit, generally. Okay, the gravity? No. Gravity of the central star? No. It can't be the gravity because the gravity is what put it on the circular orbit in the first place. It doesn't later change its mind and say, oh, I think I'll change the orbits. No, it doesn't work that way. What does work is that if you have the ability to change the energy and angular momentum and transfer it to another object, you can move. What is the other object? Well, it could be the huge gas cloud that's surrounding the star. If you transfer angular momentum to it, that's okay, that's good. Because if you transfer angular momentum, you'll sink in further. All right, if you transfer energy to something out there, you'll sink in further. You note that, that the gravitational well is like a trap. As you lose energy, you sink. You get in closer to that gravitational attraction. That's the characteristic of gravity. It attracts you. It always attracts you. It doesn't matter if your mass is positive or negative, if your elementary particles are antiparticles, it attracts you. And mass does it. That's a characteristic of how mass works. So that is characteristic there. Okay. Now, in 2009, excuse me, there was a launch of a Kepler satellite. All right, and what is Kepler doing? Kepler is an amazing satellite. Here it is. Now, the Kepler satellite, they flew a 1-meter diameter telescope, a small telescope, very small, 1 meter diameter. Okay? The field of view of this telescope is huge. It looks at 10 degrees by 10 degrees, like this. All right? Remember, a half degree is the angular size of the full moon. So this is 20 times the size of the full moon. It's big. And it has 95 million pixels on it. How many pixels are on your little camera? You know? 5. That's a lot. That's plenty. 5 million pixels on this little thing you hold up and shoot. All right, but this thing has 95 million pixels. All right, now what does it do with them? All right. Hello. All right, here is the field of view. Kepler is a special satellite that is pointing at a field of view. Here it is. This is the Milky Way. Here's Cygnus around there. And it has all these CCDs. The little triangles, or rectangles, are CCDs on it. And they're looking at these points. They're just staring at these points again and again and again. Why? Well, it's trying to look for occultations. And occultations happen rarely. Okay. Here is a blow-up of the view. There are CCD amplifiers. Some of them have died, but most of them, this is what it looks like. All right, now let's look at it again. This is one of the fields of view. You blow it up. It's on Cygnus. Here it is. Here, we're going to zoom into one part of one. This is the whole field of view. Keep going, 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 going. This star, this inconspicuous star in this field of hundreds of thousands of stars, happens to be a star that harbors occultation. And this is what it has, an occulting planet. All right, so what does it look like? This is an example of the period of this star. Here's the period in days. It goes from, this is over about a year's period of data. All these circles are observed data points. All right, and it shows, and here, look at the 9995. 9995. This is very fine differences. All right, and that is the characteristic of the noise. This is a part of dropout of data. I don't know what. Maybe they washed the instrument there, here, and here. All right, now they're going to blow up this part. All right, now we blow up that part. That's here. This is what you see. Ah, that looks like an occultation. That is an occultation. That's an occultation. This is what it looks like in detail. This is the signal. This is a comparison signal, and here it goes. The depth, the depth is it's a part in 10 to the fourth. That's what you fit to the signal. This requires very, very stable instrument to do this. Okay, so that is Kepler 10. All right, so what did you do? You saw the occultation, all right, and at the same time, you told Jeff Marcy, hey, we got a source that is occulting its planet. The occulting the star. Why don't you look at it and see what the velocity is? So Jeff looked at it. Here he's looking at it. The star is orbiting, and he measures. This is the period he measures. Not very good data, but it does fit this period. It's not very high quality data, but it's pretty small. It's a small signal. The star is moving, causing an oscillation. From this, he gets the mass per unit volume was 8 grams per cubic centimeter. What does that remind you of? 8 grams per cubic centimeter. Well, just remember, what is the Earth? If you did this and detected the Earth, you got 5 grams per cubic centimeter. All right, so this is heavy. How much is Jupiter? Well, Jupiter was 1 gram per cubic centimeter. So it's not a Jupiter-like planet. It is a Earth-like planet or a heavy planet. All right, so that is what you determine from that. Okay, the first rocky planet. This was the first one seen. So this was seen in 1990, 2000, year 2000. Okay? No, wait a minute. When did they launch that thing? 1999. Is that right? No, it hasn't been launched that long. Just a few years ago they found this. Okay. All right, now, here's the announcement that was made last year. This was pretty impressive. 1,200 candidate planets were detected. They're staring at 100,000 stars, and of them they saw 1,200 occultations on the stars. Staring, 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 staring. That's what this thing does. All right, so all right, most of them were Earth-size. This is very different, and they saw one star had 6 planets on it. That's pretty neat. One star is like our solar system that they could see. A lot of these stars have multiple planets, but unless it's oriented just right or way just right, we really can't tell that. All right. Now here's what you see. Here's what they discovered. These colored circles saw giant-sized planets, the red, Earth-sized planet, the blue. That's where they saw them. More or less random selection of stars in this in the image. There are 150,000 or more stars they're looking at. They're just looking at them all, and a few of them have stars. They have some of them Neptune-like, Earth-like, and so, etc., super Earth size, etc., etc. Okay, here's an example. Here's the suns that they saw. All right, from big stars down to small stars. All variety of stars have planets. Okay, here's another. Here's distribution of radii. This is Earth radius. Here's us. Okay, and they have others that taper out to longer size. But planets with Earth-like radii are common. Not only common, they seem to be the most abundant. So they dominate this distribution. Okay. Here is the occurrence, the number of stars, number of planets per star, down to 10 days, etc. So they have measurements of all this. You don't care about that, but here's the temperature of the planets. The temperature is determined by the brightness of the star, the proximity of the planet to the star. So here's equilibrium temperature. Remember, 0 degrees is about our equilibrium temperature. The Earth has a bunch of similar sizes, all very hot planets, 500,000 degrees Celsius. So it's very hot. And Uranus-sized planets, they're also hot. Jupiter-sized planets, they see it's easier for them to see hotter planets because they're closer. But this is the distribution they saw. They're not really, it's not obvious that those are Earth-like planets. They're not, but they are planets. Okay, this is Earth-like temperature. Some of them are. Here's one. All right. And so, okay, there's one planet they've seen so far that's Earth-like. If we take that distribution and blow it up, here it is. These are in the habitable zone. All right, and there are planets there. Now, I mean, it'd be nice if we knew more about the planets, but this is what we know so far. Here is a case of a very interesting case, a beautiful case. This is known as, well, this is, I forgot what it is, something or other. Here is Jupiter, Kepler 11, I forgot. All right, here's a drawing of our solar system with the orbit of Mercury and Venus and the Sun. And here is Kepler 11. 1, 2, 3, 4, 5, 6, 7. It has 7 planets that have been detected, all within the orbit of Venus. So it's a pretty tight system. So that's an example of what we can see in of extragalactic planets. It's kind of amazing, but they are detectable. Okay, so let's look at this case. This is Kepler 11. we happen to see this edge on for this particular planet. Because it's edge on, you could see everything at once. And they're orbiting around. Note that of course, just like Kepler's law says, the planets that are in close are orbiting faster than the planets that are further out. That is to be expected. All right, so here is a picture showing the orbits of what they've seen. Some of them moving slowly, some of them moving rapidly. They've seen everything. Every planet's just a little different. They're not all the same. You know, you can choose if you want a hot planet or a cold planet, but they're not all going to be like our solar system. Pretty neat. All right. Okay. Now, so we have two methods of detecting planets. One was the motion, the Doppler shift of the motion, and the other is the occultation of that. That means occultation is brightness changing. So both techniques are very powerful, and they lead to amazing results. These techniques, I must say, have only come into the beautiful results have only been available in the last 10 years. This is really very, very current research, and it is kind of amazing that Kepler works as well as it does, but astronomers get to look at this and have a good time with it. Now they've seen, in another case, they saw the situation of Tatooine. Everybody, do you all know what that is? Tatooine? In Star Wars, Tatooine was the name of the home planet that Luke was from. He was an orphan, brought up by his uncle. His uncle and aunt lived in a crazy place in Tatooine. It's a very sandy planet. The planet's orbiting, and they dug out. It's all below ground. Remember this? It's all below ground where they dug and went down. So he lived there. And there were two stars orbiting each other. Well, they've seen something like it. That is to say, a binary system with a planet orbiting it, just like Tatooine. Okay? This is very common. They should be very common. So, so if you want to look for Luke, there he is. Now, unfortunately, this is not right next door. These it take a while to get there. They're up to 500. Isaac, do you remember the distance of typical star seen? I think it's of order of kiloparsec, let's say. All right, kiloparsec. That means that is 3,000 light years from us. Okay, that'll take a while to get to on your little boat. So they're going to be, forget it. They're just out there some year. So you learn about the parts of the universe that we can't travel to. At least we don't know how to travel to. I can't imagine we're going to make it there. All right. Now, I suppose I should review something for the exam. Does anybody have questions on anything at all? Because we're done with the lecture. The next lecture is going to be on Einstein's theory. We're going to talk two lectures about Einstein, and you will see you will see why I don't believe this announcement that these neutrinos are traveling faster than light speed. Okay, I just find it hard to believe. But anyhow, you'll see why. Why I think something else. Any questions? I didn't have too much this morning. Everybody knows what was coming. The exam from 7 till 9, not 6 to 8, at Latimer. It's not going to be difficult. If you did the homework and got fine grades on that, you'll get very fine grades on the exam. If you understand what I'm talking about here, you'll get fine grades on the exam. All right, don't worry. This is, although this is not high school, we'll give, the course, for example, is graded on the curve, and I give typically 1/3 A's, 1/3 B's, 1/3 less. All right? But you really have to screw up to get less than a B. If you work at all, you're going to get a B in the class, for God's sakes. People who get less than that somehow feel they don't have to do the homework. That's wrong. If you turn in the homework, you'll get it. It helps. Remember, homework counts. So if you turn it in, it helps your grade. All right, if there's no more questions, let's break for today. And good luck on the exam, although I'll see you next Thursday morning. So we're going to talk about Einstein's theory.